Watch this short shower video. As you do, list on paper all the things that come to mind. So what came to mind? Having heard the things that come to the minds of many people, did yours include water conservation? Whose shower is that? Why does that person have a funnel in the shower? Why is the water blue? How did it become blue? Are the measurements on the jug accurate? Why is a timer running? One thing I was willing you to wonder about was how fast the shower was running. Is it faster or slower than when you have a shower? Or to put it another way, how fast was the water flowing into the jug? I will now show you the shower video again, and this time do what is necessary to calculate how fast the water flowed into the jug. By the way, the measurements on the jug are accurate. I'll have a go too and share my effort with you in the next part of this video. Then you can compare your effort to mine. Well, here's what I did. The more or less constant sound made by the water made me think the speed, or the rate of flow, was approximately constant. I noticed it took nearly 40 seconds for 5 litres to flow into the jug. And so based on these two observations, I figured that the rate of flow was about 1 litre every 8 seconds. But am I correct? To determine if I was correct, I collected some data. The time taken for each half litre to flow into the jug. So my idea of 1 litre every 8 seconds does not look too bad. I then made a scatter plot of these data, and as you can see, the plot has a linear nature to it, suggesting the flow rate is constant-ish. It shows graphically that in each 8-second window, about 1 litre flows into the jug, which tells me it would be fine to model this process with a linear function. So I determined the least squares line of best fit. The gradient of a linear function is the ratio of the change in y to the change in x. In this scenario, the ratio is the change in volume to the change in time, which has units of litres per second. We call this quantity the rate of flow. The least squares line has gradient 0.128, suggesting the flow rate is approximately constant at 0.128 litres per second. So how does this relate to my observation of 1 litre approximately every 8 seconds? Well, 1 litre per 8 seconds equates to 1/8 of a litre every 1 second, which has a decimal equivalent of 0.125, and 0.125 is not too far away from 0.128. So I am now convinced that the rate of flow of the water into the jug is approximately constant. We could hear it as a constant noise, see it through the 1 litre in every 8 seconds observation, and measure it by calculating the gradient of the least squares line, which gave us 0.128 litres per second. Did you wonder how the approximately constant rate of flow was achieved? Well, just turn the tap on to a certain point and leave it alone. I hope you enjoyed thinking about this situation. A different flow situation awaits our thinking in part 2. See you there.